So in the last part of this report, we are going to look into the Bose-Einstein condensate. Now, so at very low temperatures almost close to the absolute zero, so bosons, we saw that there are three types of quantum particles. One is bosons, fermions, and classical particles. So bosons, they transform into a new state of matter, which is not solid, which is not liquid, it's neither gas, but it's a new state of matter called the Bose-Einstein condensate. So let us look at the science behind this. Now, in the quantum world, we know that particles are not only particles, but they also behave as waves. In other words, the wave-particle dualism is what is followed in the quantum world. Now, when the temperature is decreased, the particles lose energy. They start dropping from the higher energy levels to the lower ones, and almost all the particles, they tend to occupy the lowest energy level, epsilon min. Now, in such a situation, the wave-like characteristic of the particles, they become very prominent, and a significant amount of overlap occurs between the waves, something like this. Now, in such a situation, the particles lose their identity. And it turns out that this entire system, it can be expressed as a single quanta of wave. So all particles, they have lost their identities, significant amount of overlap between their waves, and this entire thing can be expressed as a single quantum of wave. And that is when we say that the particles have gone into a new state of matter, and which is the Bose-Einstein condensate. So let me show you a small demo. So as you can see that as the temperature is lowered, the particles slow down and they lose energy, and after a point of time, the wave-like nature of the particles become quite pronounced. And remember that we are talking about the bosons, and at sufficiently low temperature, as you can see that all these waves completely overlap, and we can actually express this system as a single quanta of wave. Now, this phenomenon was predicted by Satyendranath Bose and Albert Einstein long back. So the discovery of the Bose-Einstein condensate dates back to 1924, if I'm not mistaken. Yes, that's right, it's 1924, when the young Indian physicist Satyendranath Bose, so he gave a new derivation for the Planck radiation law. And the way he gave this new derivation was just by reducing the problem to one of counting or statistics. So we know that for the Maxwell-Boltzmann statistics, the particles are distinguishable. But over here, we consider the particles to be indistinguishable, and that indeed was in the crux of Bose's new derivation. So Albert Einstein, he realized the importance of this derivation and for developing a quantum theory of statistical mechanics, and he argued that if photon gas obeyed the statistics of Bose, so should material particles in an ideal gas. And carrying this analogy further, he showed that quantum gas would undergo a phase transition at a sufficiently low temperature when a large fraction of the atoms would condense into the lowest energy state. Now, in the first part of the report, we saw how the plot looks like, and this is not a surprise to us from the plots, that at temperatures very close to absolute zero, the mean number of particles occupying the lowest energy state is indeed infinite. In other words, the tendency of the bosons to stay together and occupy the lowest energy level is very, very, very high. And it is because of this the BoseEinstein condensate is formed. So there's a phase transition at such low temperatures, and the Bose-Einstein condensate, that's a new phase is formed. So now how is it achieved? So in 2001, Eric A. Cornell and Ketterle and Wayman, they were given the Nobel Prize in Physics for the achievement of Bose-Einstein condensation in dilute gases of alkali atoms and for early fundamental studies of the properties of condensates. So there are a lot of ways of achieving this, and the two most common ways are using the laser technology, the laser cooling and evaporative cooling. So you can have a look at the report that is submitted to gain to have a deeper understanding of it. And what are the applications of Bose-Einstein condensates? So Bose-Einstein condensates are said to find numerous applications in quantum information processing, that is the concept of quantum computers. And there are still a lot of experiments running in this area, but definitely if we can produce Bose-Einstein condensates at a decent temperature and pretty easily, then quantum computing is going to be a field that is going to improve and advance by a huge margin, because most of the properties are shown by the particles at this state are of that of quantum nature. And the other is obviously the precision in measurements will come because there's this concept of existence of a giant coherent atom, and this should increase the sensitivity of instruments doing certain measurements. And obviously it brings together the fields of atomic physics and condensed matters, and so this is definitely another emerging field would be nanotechnology, and BC can really have a great impact on nanotechnologies. So in conclusion, the experiments using BCs, they have been truly beautiful illustrations of quantum physics.